So everyone's talking about AI agents, but what exactly is an AI agent? In today's video, we're gonna have a conversation about it by drawing a house on a piece of paper. I already have one because I did another take, but we're gonna take one and then we're gonna draw a house. So I want you to take a piece of paper and a pen and draw a house. Take like 10 seconds. All right. So when you're done, just kind of on the count of three, show your house and we're gonna both show each other our houses together. Okay, 1, 2, 3. All right. Well, this is my house. I can bet you like a lot of money that your house is very different than mine. And if you ask someone else to draw a house, their house will be the same as well. I have some houses in front of me. You can see that there's a castle. There's a banana house. Someone drew a shoe house. So everyone's drawing really different houses. So what does that tell us about the problem? The outcome is not the same, but the instruction was. Like, I told you to draw a house. I told myself to draw a house. Everyone I asked, I told him to draw a house. But why was it not the same for everyone? What does that tell us about a problem? So we're going to talk a little bit about anatomy of problems later. But we're going to try to give the same instruction to a computer. In this case, a program like a Python or a Scratch program. And the way you have to even like draw a square is like this many lines of code. Like, it's not like just draw a square, right? We'll talk about why. Well, you can do that, but at the end, under the hood, it's doing something like this. So the instruction is go to 0, 0. So the instructions is go to 0, 0, point in this direction, erase everything, put the pen down, move 100 steps, turn up, yeah, blah, blah, blah. And then you can see that it kind of draws a square after like 15 lines. And what did you notice? One thing is it's kind of like going step by step, and you have to be very precise. The idea of house is kind of lost on a computer, and we'll talk about why. And if you change one thing, like instead of 90 degrees, you put 80 degrees, it kind of messes that up. How easy it is to mess up a square, I did not know. But that kind of speaks to the volume of what a computer is. A computer is a completely different thing than a human being. The way it thinks is completely different. It's like a car. The car moves differently than a human being. Human uses muscles. Cars uses combustion. Birds use like their wings. Yeah, so airplanes use the Bernoulli principle to like fly and things like that. So there's completely different fundamental principles they're operating on. And that kind of fundamental operation is it runs one line at a time. A computer through a CPU, we'll talk about what a GPU is, but normal, all traditional computers that run programs like Python run on a CPU, and they run one line at a time. So they run like 9 billion lines of code at a time, but at the end, it's one line at a time. So that kind of speaks volumes to the code we write. It's basically like how the atoms make us up. The properties of the atom kind of dictate what materials can be made. Like if there was like a little bit of change in the atom, like the materials will be completely different. A computer has a very narrow view of the world. By that logic, it can only do very small tasks at a time, and they have to be very precise in this case. We'll talk about why, because a computer has no idea what's going on. So it can only kind of draw one pixel at a time or change memory space of one pixel at a time. So that kind of becomes a line, and that becomes a square. You have to be very precise. There's abstractions using functions, but at the end, under the hood, it's very, very precise. You have to be very precise. I remember I told this story. I asked a student of mine, he was 10, to find the number 7 in an array of numbers. And he basically is like, oh, why do I need a loop for that? Yeah, 5 is right there, or 7 is right there at the 5th position. Can a computer see the screen? So kind of speaking to the same principle of like, can a computer see the screen? No. So that's why when you're kind of writing a for loop, you have to be very, very precise and kind of look at each memory location before finding the right one. So a computer can't see the screen. Just to drive the point home is like, if you tell a computer to kill itself, it will do that. It has no inherent ability. It will do that without a doubt. So let's kind of try it. In killing it, it basically means that it's basically destroying all the memory. So in the real world analogy, it's kind of like finding Waldo through a peephole. Like basically you have to like, just have a very like tight view of the world and think about what will be possible, like what won't be possible. How would you read? Like how would you like go about your screen? Like, you find different things. How would you like kind of find people? Like you would have to look at one by one. Like let's say in a meeting room you need to find like Josh and you're like going ooh ooh ooh. That's doesn't work, right? So yeah, as I said, so we're going to talk a little bit about how you will try to get groceries by looking through a peephole, and you can see how you have to instruct a computer and how the problem space gets really, really interesting. How would you read a book? How would you drive to groceries? Humans are kind of more flexible than computers, as we kind of made sense, and that kind of dictates this house making ability. Like we could just make it very instantly, but if you're using a computer, which is like a program such as Scratch or Python, it kind of takes really, really precise instructions. And that kind of will tie up into how AI agents get their kind of flexibility of thought, where they can solve really, really complicated equations or problems that are very, very like super open-ended and could have multiple ways of solving. But we'll talk about that in the end. But I want you to be patient because in order to explain AI agents, I have to help you understand the fundamentals. You can't learn calculus without learning addition, right? So yeah, so in the next video, we're going to be talking about the anatomy of a problem and how not all problems are kind of made the same. And we'll do that by going to the grocery store. So I'll see you in there.